In Chapter 12, we're going to move out of two-dimensional geometry and into the three-dimensional space, where we're going to explore solids, not just flat figures. There's a lot going on in this world, and we're only going to scratch the very surface of it. So if this is something interesting to you, maybe it will inspire you to go out and learn more on your own, because there's a ton of stuff that you can look into and explore with these shapes. And I just want to make you aware of their existence more than actually teach you everything about them. So we're going to start with definitions and terms for 3D stuff. Polyhedron is kind of like our equivalent of polygon. So a polygon was a two-dimensional shape, and a polyhedron is a three-dimensional solid, but there's a lot in common between them. In fact, the meaning of this is a solid that's bounded by polygons. So all of the faces of it are going to be planar shapes that are polygons. So, for example, a cylinder, which you know about as a 3D shape, has a round edge, so like a can, and this rounded face, the lateral surface area of it, excludes it from being a polyhedron, just like a circle is not a polygon. So a polyhedron specifically has all of its faces that are polygons in shape. So it encloses a region of space, and then we'll do some more understanding of the parts of it. So faces are the polygons. Maybe this is faces. I don't know what goes there. But the faces are the polygons that enclose the shape. So each of this orange, red, blue, each of those is a polygon, and each of those is a face of the shape. I'm sure you're familiar with that idea. Edges are the line segments. So, line segments that are formed at the edges of the faces. So right here between the orange and red, this line segment is called an edge. And then vertices are basically the same as they were in 2D, but now they're going to be, so a vertex in a polygon was everywhere that two line segments met. So there were always going to be exactly two. But in a 3D shape, we're going to have three or more edges that intersect, and you could maybe call that a corner in commonplace language. So let's look at examples here. We have this triangular prism. At this corner right here, this vertex, there are 1, 2, 3 intersecting edges. But we could have more than 3. We could have basically any number. So if you think about like a pyramid, I'm not good at all at drawing 3D shapes, by the way. So we have a pyramid that's something like that. So just go with me. It's a square pyramid, we'll pretend. This apex point right here is going to have as many edges connected to it as there are faces on that pyramid. So for a square pyramid, there's 4 edges meeting at this apex. But if I drew like an octagonal pyramid, which I certainly can't do, but I'll just draw like the base. So if I have an octagonal pyramid that goes up to a point, then each edge is going to connect down to that base. So then that apex point at the top would have 8 edges connected to it. So that's why it says 3 or more, because it could be any number. All right, we have a thing called Euler's theorem. So Euler is a very important mathematician. You'll learn, if you haven't already, about a thing called E in math. It has a lot to do with exponential functions and exponentiation and logarithms. And that E is Euler's number, so that's the E that we use there. So Euler, big math dude. This theorem says the number of faces, vertices, and edges of any polyhedron will always have this relationship. So let's look at the ones that were up here and say, okay, we have a cube. We know that a cube has 6 faces. If we count the number of vertices, there's 4 on the orange face, and then there will be 4 more on the bottom face that we can't see. So vertices would be 8. And then edges, we have 4 around the top, 4 around the bottom, and then the 4 vertical ones connecting the top and the bottom. So that's a total of 12. And this formula says that we should be able to say 6 plus 8 equals 12 plus 2. And that's true. 14 equals 14. And that'll be true for any polyhedron, no matter what it is. This dodecahedron, this triangular prism, they'll all follow this formula. So we'll do one more. Let's do this pyramid that I drew, because it's a pretty different looking thing than the rest of these, but it's still a polyhedron. So if I counted faces, there's 4 lateral faces and 1 base. So there's 5 faces. What's next? Vertices. So there's 4 vertices around the square base, and then this one at the top, so that's 5. And then edges, I have 4 around the bottom, 4 going up to the vertex, so that's 8. And then the equation says F plus V equals E plus 2. 5 plus 5 equals 8 plus 2. 10 equals 10. Yes, so that is a polyhedron. So yeah, we have this formula, just basically tells you if something's a polyhedron or not based on those properties. If we have a solid with 6 faces, 8 vertices, and we want to find the number of edges, that would be 6 plus 8 equals E plus 2. So we actually just did that one here. 6 plus 8 equaled 12 plus 2 for a cube. So that means that this would also be a cube because we have 12 edges. So edges equals 12, and then this would be some kind of cube or rectangular prism or something like that. So we could draw a box shape. And again, I am not good at drawing 3D things. But yeah, we would have that number of edges, faces, and vertices. So surface you're familiar with because you've learned about surface area before. A surface is the set of all points on the faces of a polyhedron. So if we add up all of this face plus this face plus this face plus this one, all of those together make up the surface of that shape altogether. Let's erase that. Okay. So convex, we saw this word with polygons. So remember, a convex polygon, we had several ways of defining it, but one of them was that when we connect any 2 of its vertices, the diagonals all remain in the interior of the shape. So if I connect all possible diagonals throughout the entire shape, all of them are 100% inside the shape. There's a similar definition for convex polyhedrons, is that any 2 points on its surface can be connected by a segment that lies entirely inside or on the surface, the faces or the surface of the polyhedron. So if we have a polyhedron that has any kind of concavity to it, where it's not convex, then there'd be a way to connect something on the outside of it. So imagine if I drew just to make it really simple, if I drew a concave polygon and then made it 3D, so just turned it into a prism version of itself, then I'm going to be able to connect points across empty space. So these points would not go through the interior. Whereas on this one drawn here, which is convex, any point that I pick anywhere on it, to connect it to any other point will always pass through the shape and won't go outside of it like these edges would, or like these connecting lines would here. So very similar to the idea of a convex polygon, it's just in 3D. Regular polyhedron, similar to the idea of a regular polygon. A polyhedron with all faces that are regular polygons. The same number of faces meet at each vertex in the same way. I guess since we're meeting at a vertex, this would be edges. Same number of edges. So we've seen some of these, like these things are the regular polygons. There are only 5 of them in 3 dimensions. So again, if you're interested in going deeper with this, you can look at going beyond 3 dimensions and talk about 4-dimensional regular I guess they're not polyhedrons anymore, whatever they'd be in 4D. So these things are called the Platonic solids. So in Greek philosophy and mathematics, Plato was a big dude. So Plato is the name of this, where we get Platonic. And notice down here we have Archimedean solids. Plato and Archimedes were both pretty big, ancient, like philosophers and mathematicians. So these 5 shapes are the only ways to make regular polyhedrons in 3 dimensions. One of them, the first one, is really simple. We call it a cube. But giving it like a hedron kind of name, we can call it a hexadron or cube. The second one has 1, 2, 3, 4, 5, 6, 7, 12 faces. So we have 2, 4, 5, 6. Yeah, 6 and 6. So that, if you remember from polygons, 12 sides is a dodecagon. So this is just called a dodecahedron. This next one is all triangles, and it has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 sides. So this was 6, this was 12, this one is 20. We call that one an icosahedron. This one has 1, 2, 3, 4, 5, 6, 7, 8 sides. So that would be an octahedron, just like an octagon. And the last one is the same shape as a triangular pyramid. What even do we call a 4-sided polyhedron other than a triangular pyramid? So kind of like Tetris, we use tetra as a prefix meaning 4. So we call this a tetrahedron. It's also a triangular pyramid. So kind of like cube is a more normal name for a hexadron. Triangular pyramid, I think, is a more regular name for tetrahedron. So these shapes, if you are into like tabletop gaming, like Dungeons and Dragons and role-playing games and stuff, these probably seem pretty familiar to you because these are mostly the types of dice that you roll in those games when you're trying to do certain tests or attacks or whatever. So looking at a set of D&D dice, they're sold in sets of 7 dice, and we had 5 Platonic solids. So first thing to note is that this one is a D10, a 10-sided die, and this one that's counting up from 0 to 100 is also a 10-sided die. So we have a repeat. And if you remember over there, we didn't have 10 as one of the options. But since we count in a base 10 system, so we had 4, 6, 8, 12, 20, those are the numbers that form perfect regular polyhedrons. But since we work in a base 10 numbering system, it kind of makes sense that we would gravitate toward something that has 10 sides. So this shape, you can see, doesn't have regular faces. So the D20 right here, which is our icosahedron, has all triangular faces. Our what one is this? This is 12. Our D12 has all all pentagonal faces. And our D8 over here, our octahedron, has triangles, and our D4 has triangles. Our D6, of course, is a cube and has square faces. So all of those have these regular, either square, triangle, or pentagon faces. But then our D10 is kind of weird. It has these almost kite-shaped faces. So they're definitely quadrilaterals, but they're definitely not regular either. They're very far from being squares. And they're kind of offset from each other, right? Like where the point of this one is opposite of where the point of this 10 face is. So kind of a strange shape that's cobbled together to be semi-regular and give us a way to have a 10-sided die, but not actually one of those Platonic solids, which is why it looks kind of weird. So we have these 5 regular polyhedrons, platonic solids, and then we have these 13 other shapes that are called the Archimedean solids. And these we could think of as being like semi-regular. So in Archimedean solids, we have a combination of different shapes, and we have faces that consist of one type of regular polygon, and the same number of each type of face meet at each vertex. So basically think about any vertex on this thing. So this one right here is a meeting of 2 hexagons, octagons, 1, 2, 3, 4, octagons, and 1 triangle. This one is a meeting of 2 octagons and a triangle. And every vertex that you pick is a meeting of those exact same shapes. So there's some terms you'll see in these shape names. So like truncated is one where we have cut off the corners. So think of this, if we didn't have these triangles, this would be a cube. But what we did is we took that cube and we sliced off all of the corners to make these triangular faces. So this is basically cut off at the corners, is truncated. Rhombi is like rotated, I think. I don't really know. This is beyond where I go in 3D shapes. So you can see that these shapes, like if we look at this pattern here and this pattern here, they're like rotated relative to each other. And then snub is like rounded off, I think. So basically like the corners are rounded. I don't know how that works since there's nothing actually round, but that's like what it means is rounded corners. So these are all kind of like ways to modify these shapes, and we won't go beyond this general idea of the terminology, but there's lots of stuff you can do with these. So one interesting thing is like soccer balls are what we call a truncated icosahedron. So icosahedron was our 12-sided shape. And if you think about that 12-sided shape, it was all pentagons. And what we're doing here is slicing off each corner, and we end up making pentagonal and hexagonal alternating shapes. So a standard soccer ball, is a combination of hexagons and pentagons, and you could think of it as being our 12-sided shape, this one up here, the D12, and then basically at each corner slicing off a bit at a flat, so like slice off each of these, and it's going to form an extra face that will be a pentagon, and what's left in the middle will be a hexagon. There are other ways to make soccer balls, though. You don't have to just use that standard hexagon and pentagon pattern. So you can find lots of different designs for soccer ball patterns that are all kind of repeating patterns like these, but are not all this standard one. So we can use squares, pentagons, triangles, rectangles, and a different, like whatever combination of shapes to make the kind of pattern overall that makes a soccer ball. So another interesting thing with 3D shapes. All right, so the last thing we have here on this page is cross-section. Cross-section is a really important concept that you'll see going forward in math, and especially if you do anything with engineering or design, cross-section is super important. The idea of taking a slice through something and looking at what's going on inside as you slice it. So if we took this square pyramid and we made different cuts through it, we're going to get different shapes. So a cross-section is the intersection of a plane with a solid. And if you have ever seen engineering drawings, a lot of times we have cross-section views to show you kind of what's going on inside of a part, or to show you a kind of view of things that are cylindrical or solid that you can't really see into normally. So if we cut through this pyramid kind of flat parallel to the ground, we get a square no matter where we cut through it. If we cut through at an angle, we're going to get some kind of a trapezoid, and what angle we cut at is going to change the kind of, the aspect ratio of that trapezoid. It's going to make this side shorter if we lean it up more, or flatter, getting closer to a square if we lay it down more. So this angle right here is going to determine the nature of that trapezoid. And then if we cut through vertically, like straight up and down, we're going to end up with a triangular shape. So different cuts make different shapes as you look through it. So we have some practice here with just identifying this vocabulary and these concepts. For determining whether it's a polyhedron, we're going to use that Euler's formula equation, and that one was the one that said F plus V equals E plus 2. So if that's true, then it's a polyhedron, and if not, then it's not. So here we have a cylinder. We said cylinders don't have all polygon faces, so not all polygons. So that's not a polyhedron. This first one, we have 1, 2, 3, 4, 5, 6, 7. So that's a heptagonal pyramid, and it has 8 faces. It has 8 vertices. Pyramids are going to have those two the same. And then our edges, we have the 8 going, or the 1, 2, 3, 4, 5, 6, 7 going around up to the vertex, and 7 going around the base. So that's 14 plus 2. 16 equals 16, so that is 1, and that's our justification. We can do the same for number 3. Euler's theorem we can use for these as well to find a missing value for those polyhedrons. This wants you to sketch some polyhedrons. I'm not going to try that. Just remember that pyramids go to a point at one end, whereas prisms have all rectangular lateral faces. So you have 2 identical bases and rectangles connecting them. And then regular tetrahedron we saw in our notes. This one wants you to find the faces, vertices, and edges of these, and then verify that you counted correctly using Euler's theorem. So count them up from the drawing. For example, let's look at the Z shape. We have up on the top part of the Z, 1, 2, 3, 4 faces going around, and then 1 on top, so that's 5. Then we have 1 underneath. That's 6, so that's like the whole top part. Then coming down on the sloped part, we have, well, I guess this front face is all one face. So let's try to number them. Okay, 1 is the top, 2 is the back, 3 is the left side, 4 is the front, and 5 is the right side. So 1, 2, 3, 4, 5. And then underneath the top will be 6. So 1 and 4 covered the entire front and back. But coming on this slope down, we have 7, 8 for the left and right faces. Then at the bottom, we have 9 is this left face, 10 is the bottom, 11 is over here, 12 is up on this top part. And again, the back is already covered because 1 was the entire back. So it looks like, and I haven't actually done this one, so hopefully we get this right. It looks like there's 12 faces as far as I can count. And then we have vertices. So I'm going to erase what I did here. And vertices, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then finally, we need to look at edges. So I actually think that in like looking at a 3D drawing in 2D, the hardest thing to look at is the faces because they kind of overlap where they're in front and in back. The vertices and the edges are actually a bit simpler. So here I can just kind of go around and highlight my edges. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So 28. So does 12 plus 20 equal 28 plus 2? I don't believe it does, meaning I counted something incorrectly. I got 32 versus 30. So just to kind of finish up for today, let's try to figure out where I counted incorrectly. All right, vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I'm pretty confident that's 20. Edges, I'm less confident. So I'm going to start from top and head down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Pretty confident that that covers the top. Then 14, 15, 16, 17, then 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I'm confident I've missed one somewhere, because that's got to come out to be 30. 29 doesn't make sense as being an odd number. So, if you can figure out where the one I missed is, or if you're shouting at the screen saying, why are you missing this one? I don't know, it's just hard to see sometimes in 3D. So, yeah, I don't know. I think I'm going to call it there. No, not there. Yeah, I give up on this one, but I'm confident that this should have been 30 and that I just counted incorrectly. So if you can find the one that I missed, that's good for you. That's pretty much it for today, is just practicing that theorem, and then here identifying the other vocabulary like convex, concave, regular, the kind of stuff we were just talking about. And then the rest of the chapter is going to be more familiar kind of stuff, like I said, really basic, where we're going to do our kind of basic shapes, prisms, cylinders, cones, all the stuff that you've seen before. I do want to mention, since it has this picture, one of the reasons that the idea of a cross-section is important. So if you look at number 20, we have a cone, and one of the things you'll get to later in math is a concept called conic sections. And this is a good place to kind of look at that. So if we have a cone, we can slice through it different ways. And if you slice through a cone perfectly parallel to its base with a plane like that, then our cross-section is going to be a circle. But if you tilt the plane, you end up with an ellipse, which is kind of like a stretched out circle. But if we make it vertical, so if we slice through this way, we end up with a parabola. And if we kind of, usually when this is shown, there's two cones, so it's like this. If we slice through at a certain angle, we get a parabola, and then if we slice through both cones, we get a shape called a hyperbola. So there's a bunch of things that you've seen before and will see that are kind of in a class of shapes called conic sections. So yeah, that's pretty much it for 12.1. We'll go into our stuff that looks more familiar, like surface area and volume, starting in the next section.